Chemistry, this is the answers video for day 66 collisions. It's the third lesson in the kinetics unit. Okay, so it says it's due Friday, December 9th. It doesn't have a not accepted after date, so we're going to make that Friday not accepted after is going to be Friday, December the 16th. You do have a quiz on this on that day. All right, here we go. So sketch, this is just kind of a review. Sketch without numbers, 0th, 1st, and 2nd order. So 0th order, concentration of A versus time is going to be a negatively sloped straight line. So concentration versus time, it doesn't matter what the concentration is, how high or low it is on this line. The rate is going to be the slope of the line, and that's going to be constant. Wherever you are, you're going to have the same rate, the same slope. So that means it doesn't change. So to linearize it, well, you don't need to do anything else. I'll just write it a second time, and that's going to linearize it, so those are the same. Okay, now we go to first order. First order is going to be a curve that looks like this when you plot concentration. The graphs on the left are all concentration versus time. Okay, to linearize it, you plot the natural log of A. Again, all you need to do is know how to use the ln button on your calculator to get those numbers, all right? And versus time, and that's going to linearize it. And again, the slope is going to be k. K is going to be the negative of the slope. So the slope is negative. K is always a positive number. All right, so that's what that's going to look like. Now if we do the concentration of a second order versus time, it has a slightly different shape than this, but it's almost undetectable what that difference is. It's a little bit steeper, curves a little sharper, and it ends up a little bit flatter like that. So that's what it would look like. And now if you linearize that, the way you do it is you don't need logs this time. It's just 1 over the concentration of A versus time, and that's going to give you a positive line. So the slope, so this is K, the slope equals, or K is the rate constant, equals positive slope. So there's no negative sign there. It's a positive slope, okay? And over here it's also K equals the negative slope. Right there. Okay, that's all you needed to do there. All right. Be sure you know how to get those, how to recognize those. Okay. Sketch a potential energy diagram for an exothermic and endothermic equation with explanations of each part of the graph. Identify activation energy and total energy in the energy reaction. Okay, so we're going to start with exothermic. It's going to start right here with some reactant. You can just say it's a single reactant A. It's going to go up. It's going to come down. And the energy level over here for product B is going to be lower. Okay, so this is the activation energy, EA, is the difference between, this is energy on this diagram, and this is time as the reaction runs. So the energy, the activation energy is EA. It's the difference between the energy level that the reactant was at and how high it has to go to get over this hill. So you have to give it this much energy to get it up over this hill so it goes down to reactants. If you come over here, this is the difference in energy, the change in energy, delta E. It goes from where the reactants were down to where the products are. It's lower energy, so that means energy comes out. That's what that arrow represents. Energy comes out of the reaction in the form of heat or enthalpy. Okay, delta E in this case is delta H. And it's negative because it's coming out. So that's a negative enthalpy right there. Okay? All right. If it's endothermic, we could start here. We could go up the same way, and then we come down to here. It ends up at a higher energy level. So energy had to go in. So again, the activation energy would be the same here in these two cases. But the difference in energy, delta E, change in E, equals positive delta H, meaning that heat had to go in. Remember, delta H enthalpy is the heat that goes in, all right? And EA, activation energy. Write that down if you're not familiar with that. Okay, sketch Maxwell-Boltzmann distribution of a reaction at 100 and 1,000 degrees centigrade. So this over here is number of particles. That could be atoms or molecules. And this is velocity, which is a function of temperature. The higher the temperature, the faster the molecules move. So 100 degrees is going to look, let's put an activation energy, by the way, in here. So this represents the activation energy, EA. So 100 degrees is going to do this. And so this is 100 degrees centigrade. So none of the particles reach activation energy. That means the reaction doesn't take place. I'm going to write that, no reaction. Okay, for the 1,000 degrees, it's going to go like this. Okay, so this is 1,000 degrees. So the shaded area is particles that reach activation energy is this here, this shaded region, because they pass this dashed line. So at 1,000 degrees, you have a good portion of the particles reach activation energy. At 100 degrees, there's not enough energy, not enough velocity for them to hit each other hard enough to break apart from each other, and so you don't have any reaction there. Okay, come down here. Sketch a graph of rate constant K versus temperature. So it looks like this. So as temperature goes up, K goes up at an increasing rate. So the slope here is steeper than it is here. So if you get to higher temperatures, the K value will go up even faster than it does at lower temperatures. Okay, I'm going to write that. All right, move on. Okay, write the Arrhenius equation. Okay, that's in the lecture video, so I'm not going to do that one. It's the K. It tells you what K is a function of. K equals A, which is frequency factor, times E, which is Euler's number, raised to the power negative EA over RT, which is the gas constant. Okay, so you can see that one in the lecture video. Watch that. On this one, I told you there was an error. This should have been 273K, and this one should have been 308K. All right. So we want to find out, here's what it says. The value of the rate constant K is 1.35 times 10 to the negative fourth at 35 degrees. So this is correct right here at 308. So what it's saying is that K1 is this number right here at certain temperature, which is 308, which is T1. The activation energy is this, 102,000. What is the value of the rate constant K at 0 degrees? So if you have this is, or 273 Kelvin, you got to always be in Kelvin. So you plug this in Kelvin there, and that will give you K2. That'll tell you what your new rate constant will be at that temperature. So I'm going to do this one. And let's see, so we plug in the numbers. Okay, so I'm going to come down. This is really just a plug in the numbers problem, but it's a little bit challenging. So we're going to use this formula. So natural log. K2 is what we're looking for. That's our unknown. There's K1. Negative. Activation energy is that. Okay, and R is, we have to use the alternate R value, gas constant value. It's joules. By the way, this should be joules. Joules. Okay, now we're going to put in 1 over T1, excuse me, T2. The new one at the new temperature, T2, is 273. Okay, we know the rate constant at 308. That's T1. Got to be sure you get those in the right order. Okay, so that's what it looks like. So how would you solve this? I would recommend that you do it one step at a time. Don't try to do too many steps. So I would do this. So I'm going to show you how I do this. It's very simple. If you do PEMDAS, order of operations, 1 divided by 270 minus 1 divided by 308. It's going to do the divisions before it does the subtraction, and that's what you want it to do. You want to get this division, then this division, and then you want to subtract this one minus this one. So I'm going to do that. You don't even need parentheses for that. 1 divided by 270. And that should be 273. Probably caught that. Okay, so let me start again. 1 divided by 273 minus 1 divided by 308, and that equals 0.00042, we'll call it. So this is 0.00042. Okay, times this. So I'm going to go ahead and multiply this times this, times 102,000, try to do this so you can see it, divided by 8.31. Okay, and so what I get is 5.1. I'm just going to stop there. So this is negative 5.1. All of this right here is that. That's going to equal natural log of K2 over this. Okay, so what do we do to get this out of the log? You say E raised to the K2. I'm off screen. Anyway, okay, I just said E raised to this power equals E raised to the negative 5.1. So this you do on your calculator. So this simply becomes, I should have put the ln there. Okay, so this whole thing becomes the exponent. So this becomes simply K2 and e to the negative 5.1. I'm going to do that. So it's second ln gives you e raised to a power, and it's negative. Use this for your negative down here, not the minus sign. Okay, negative 5.1, close parenthesis, and you get this. Okay, I'm just rounding it right there. Okay, so now you're going to multiply both sides by this. This cancels. And now you have K2 equals this. So that's the new equilibrium constant at 0 degrees. So it's going to be that times times 10 to the minus 2. And that's going to equal, and this is what I get. I get 8.2. I'm going to put it in scientific notation when it's that small a number. 1, 2, 3, 4, 5 times 10 to the negative 5th. Okay, and I'm not going to worry about units of measure. Let's just go with the number here. So notice that this number is smaller than, got this all over the place here, than the number we started with. That rate constant is bigger than the one we have down here. Why is that? Get this in focus. It's because we started at 35 and we wanted to know what the rate constant would be at a much lower temperature, 0. That means the K is going to be less because you have lower temperature, so you have a lower value of K. All right, that's how you do that one. Let's do this one together. Be sure you know how to do these. Okay, you get one of these on the test, you can't copy anything. You're going to have to know how to do it. Okay, so here we go. All right, same thing. We're going to plug in the numbers. See if you can do it first before you just copy. Okay, so we're trying to find the K2. So our initial temperature is 45 degrees centigrade, and there's our K1. So we want to know at T2 is 10 degrees centigrade. This is the Kelvin conversions. What is the equilibrium constant going to be at 10 degrees? So you know it's going to be lower because you start off at a higher temperature. You want to know what it is going to be at a lower temperature. So that means K2 is going to be lower. The reaction is not going to happen as fast at a lower temperature. So let's go ahead and do this. I'm going to do this quietly. So again, I'm going to do this calculation first, and I'll show it to you. 1 divided by 283 minus, because it's going to do the division first, 1 divided by 318, because it's going to do that division first. Okay, do them at the same time, and then it's going to do the subtraction, which is what you want. So you hit that, and you get this. Okay. Now you're going to take this and multiply it. This takes the place of that, so you're going to multiply by 100,000 and divide by 8.31, and it gives us 4.68. So this whole thing, negative 4.68. Again, I'm not worrying about units of measure here. It's going to be a rate constant, and it's going to be whatever, first order. It's first order because you have seconds to the -1 there. Okay, so here we go. Okay, there you go. Now we're going to raise both sides e to these powers. Okay, these two cancel each other, so you just end up with K2. You do this on your calculator. Second natural log, which gives you e to the x. There it is. And it's negative 4.68. Close the parenthesis. Boom. And it's 0.0093, I'm going to call it. Now we multiply both sides by this. And we do that so that these will cancel. So now we have K2 all by itself on one side of the equal sign. So the last step is just to multiply this times this. I already have this on my calculator right there, so I'm not going to erase that. So it's times 1.25 times 10 caret negative 4. And that's going to give us this. And that's going to equal, in scientific notation, 1, 2, 3, 4, 5, 6. 1.16 times 10 to the negative 6. It's 1 over seconds because that's what we started with. Okay, so if we compare that to our original rate constant, at a higher temperature it was 10 to the -4th. At a lower temperature it's 10 to the -6. That's a much smaller number. And so therefore the rate constant went down. So that's the value of K. K equals this. Okay, that's how you do this. All right, the last few problems, again, you need to understand how to do these. Don't just copy them. I'm going to have you just plug into the Arrhenius equation some different numbers and see what you come up with. So for this first one, K equals, A is 3. And don't worry about units of measure. E raised to the negative EA, that's negative 10,000, over RT. There's the R. You have to use the 8.31, not the 0.0821. I'm not going to put units of measure, just clutters up the page. And T is temperature in Kelvin, 300. Okay. So this one's a little bit tricky to do. Okay. So all that's in parentheses there. Okay. All right. So here we go. We're going to do this first. Here's what I would do. I would just do this number first and then write it down. So that's what I'm going to do. So it's simply going to be 10,000. I know it's a negative, divided by 8.31 divided by 300 equals. Okay. And it's 4. So I'm going to put a negative in front of that. So I'm going to rewrite this as 3e to the negative 4. Okay. All right. So now you just do e to the negative 4. So second natural log, negative 4, close the parenthesis, gives us this number right here. And now you're going to multiply this number by 3. So times 3 equals, and we get this. So the rate constant K, let me write it so it's clear what we figured out. K equals 0.055. Okay? Now I'm going to have you change one variable in the next couple problems to see how it changes. So let's come over here. Now what did we do here? Let's compare it to this. So everything's the same except we went from 300 degrees in temperature down to 100 degrees. So that ought to make the rate constant go down because we're now doing it at a lower temperature, so the reaction is not going to run as fast. So let's go ahead and do this calculation. Everything else stayed the same. R is the same. What changed is temperature. It's now 100. So we ought to get a lower value for K. So let's see what happens. Again, just go ahead and do this first. 10,000, I'm not showing it on the screen, divided by 8.31 divided by 100 equals, and I get 12. Okay, so it's going to equal, K equals 3e to the negative, don't forget the negative sign, 12. Okay, so now I'm going to raise e to the minus 12, so second natural log gives me e. Then I put negative 12 in there, close the parenthesis, equal. I get that number, and I'm going to multiply it by 3. And that gives us that number, so K equals, there you go, 0.000018. So you see this number, K, is much smaller than the K we got before. By lowering the temperature, we lowered the value of K, which means the reaction is going to run slower. Okay, now we're going to change one other variable this time. We're going to take the temperature back to 300 from the original problem. Everything stays the same, but we're going to double A. Well, you can kind of do that one in your head. I'll go ahead and set it up. K equals, do it in your head, are you kidding? E to the negative 10,000 over 8.31 How the heck do you do that in your head? Well, look what you did. You doubled this number from 3 to 6. That's the only thing you did. You didn't change anything else. So that means that the answer you got in part A is going to be 2 times that. Okay? So that's going to equal 0.110. Okay. Okay, and so you see if you double the frequency factor from 3 to 6, you're going to double the K because it's just a straight linear relationship. Okay, what happened to the rate constant in part A? I didn't answer this. It went down. Well, I did. It went down. What happened to it here? It went up. Why? You double the frequency factor. How often the molecules are hitting each other, you're going to increase the rate of the reaction. Okay, that takes care of this answers video.